everybody. This worksheet is week 4, which is on Gauss's Law. And in this case, the problem that we deal with is a spherically symmetric charge distribution. And what Gauss's Law tells you is, or what it does, is it relates the flow of electric fields through some given closed surface to charges enclosed by the surface. And the flow of electric fields is something that we normally call flux. So what this does is it relates flux, electric flux, to charge enclosed, and a really useful relationship. And it tells you that through some closed surface, the flux, the electric field, is equal to the amount is exactly equal to the amount of charge that's enclosed within that surface. Meaning, and that's the thing with you when you apply Gauss's law to a system, that surface that you pick is not arbitrary, but you're allowed to pick it, and you want to pick your Gauss surface typically to match the symmetry or the surface of the object of interest, which has a charge on it. So, for example, in this case, we have a spherically symmetric charge distribution. So the charge is distributed within spheres or shells, where a shell is just a hollow sphere with some thickness. And since the objects with the charge are spheres, when we pick our Gauss surface to figure out electric fields within each part of this problem, through each part of the space, we want to pick our Gauss surface to match the surface of interest. So that means we want our Gauss surface to be spherical as well. And so if we had a different shape, we had, say, charge distributed through some right cylinder, which, say, it's like a wire, and we approximate that as a right cylinder, then your Gauss surface, if you want to get electric field due to that wire, you pick your Gauss surface to be a right cylinder as well, and you want it to enclose the entire shape. So in the way we do this is because we want to be able to deal with a system where we can simplify the problem where the electric field is uniform over our surface of choice, which would mean that per area element over the surface, the Gauss surface, the flux is the same at any point along the surface, meaning the electric field is the same. The amount of electric field flow through each part of any area element you pick along your Gauss surface is the same. And if that's true, then when you have this relation up here for Gauss's law, you can pull out the electric field out of the integral, right? Because like any function, vector function, if it's not a function of the argument of the integral, you can pull it out of the integral. But just remember, the important point when you pull out the electric field out of here, sorry, it's super shaky, is that you have to be able to, you can only do that when the electric field is uniform over the surface, which isn't necessarily always true. But in this case, it will be. So in this case, we have a insulating sphere of radius A inside a shell with thickness C minus B. And that shell itself, so this area, is a conductor, and then this is an insulator. So we can immediately say, since we're dealing with an electrostatic problem, that this insulating sphere of radius A has some electric field inside it because it has some charge in it as given by the problem, and that the electric field inside this shell is going to be 0. Because remember, any conductor in a static electric field, in the presence of a static electric field, will have no electric field inside of it in the static situation. And that's because in the electrostatic situation, we're in an equilibrium state, and so there's no charges moving. That's why it's electrostatic. No charges are moving. The charges have already distributed themselves in a way to have no electric field inside the conductor. So immediately, because we're going to want to solve for an E field outside of this sphere, so the electric field where the radius is greater than the biggest radius of the sphere of the shell, which is C. So there's going to be an E due to some charge distributions within the shell and the insulating sphere. So that's going to cause some electric field to be out here. And there's going to be an electric field inside the shell, which we just said is equal to 0. Then there's going to be some electric field inside the shell, but outside the sphere. And then there's going to be an electric field inside the insulating sphere as well. And that's when R is less than A. This is when R is in between B and A. And then in between, in the shell, it's when the radius is in between B and C. And then outside the whole system, the electric field is a function of the radius. Well, the radius in this case is greater than the outer radius of the shell, which is C. So what we want to solve for this problem is get the electric field for each section of this object. We're given some things. We're given the charge that's spread on the insulating sphere, and we're told it's uniformly spread through its volume. So if the charge is uniformly spread throughout the volume, that implies that the charge density, rho, since it's a volume, we usually use rho, is constant. So that means throughout the volume, meaning if you were to take a derivative, say with respect to the radius of this charge density, where R is less than or equal to A, that the charge density spatial derivative is equal to 0, right? That's just saying, so this is just saying, that the charge density is constant throughout the volume. And that's true because the charge Q1 is uniformly spread throughout the volume, meaning no matter where you look within the sphere, insulating sphere, the same amount of relative charge exists at any point in it. And that implies that if you're moving through that sphere with a radius, then that value won't change. And that is the derivative of the charge density with respect to radius would be equal to 0. So it's important to make that point, because if the insulating sphere, say, had a total charge in it, but it wasn't uniformly spread, this would be a more complicated problem. But in this class, I think for the most part, we just unless we're dealing with point charges, we're dealing with uniformly distributed charge distributions. Okay, so that's one thing to realize, what that implies. And then we have a concentric shell, which is a conductor, which we already said, that electric field is going to be 0, and that spherical shell has a net charge on it of negative 1.5 coulombs placed on it. So, the thing to realize here is inside the shell, the electric field is 0, but there is a net charge on it. So that means however the charges distribute within the shell due to the external field, the field due to the insulating sphere permeating through it, will cause the charges to distribute within the shell in order to allow the electric field inside the conductor to be 0. Meaning, if we look at one section of the shell, say we take a little slice of the shell, and then inside here is going to be our insulating sphere. And we know this has some net positive charge of 3.6 microcoulombs. Because there's some positive charge within this sphere, it's going to emit an electric field, right? Radially outward. And that will permeate every slice of our conductor shell. where this is our conductor shell. It's an electrostatic situation. So the electric field inside is 0, but there is a non-zero electric field which is permeating through the conductor. And so in order to keep the electric field inside this conductor as 0, the charges within this shell, within this shell, have to distribute themselves in a way in order to cancel out this. One way to think of it is like to cancel out the net flux of the electric field caused from the insulating sphere. So you can almost think like it's not exactly true, but it's a good way to think how the charges inside the conductor will distribute themselves in order to cause a electric field in the opposite direction, the same magnitude of the electric field external to it caused from the sphere that goes through the shell. And so in order to do that, charges would distribute themselves in a way inside the conductor to cancel out this field. Well, inside a conductor we have free charges, so that means that the charges can move however they want. And so what they will experience, thinking Coulomb's force law, some radial force due to some positive charge distribution on the sphere in here. And so any relatively negative charges will want to move towards this positive charge, and they will start to build up on this inner side of the shell. And since Coulomb's force law is a radial force, and this is a radially symmetric object, they will distribute themselves all along this inner shell. But once I put positive signs. Once these relatively negative charges distribute, the point in which they stop building up on this inner shell of the inner radius of the shell will be the point at which the relative charge difference between a positive charge on the shell and the inner radius of the shell's charge will have to be equal in magnitude, but opposite in sign. Because at that point, it'll reach some sort of equilibrium where no more negative charges. It'll be more energetically favorable for those negative charges to now start to stay further away from the inner shell. And that's the equilibrium condition. But if on the inner shell there's a charge distribution with a equal and opposite charge to Q1, so now this inner shell will have a total positive charge of negative Q1. That leaves relatively positive charges on the outer shell. But we know, so what is this? Q at radius C. What's the charge on the outer shell? That's something we'd have to figure out. But we know that the total amount of charge on a conductor is conserved. And we're given that the total charge in a conductor is Q2. So no matter how much, which is negative 1.5 microcoulombs. So no matter how these charges inside a conductor distribute, the total still has to equal the net charge due to charge conservation. And we know that the inner shell is just negative Q1, and then the outer shell is what we need to solve for. And so we can then solve that Q on the outer shell total charge would be equal to negative 1.5 microcoulombs, and then I can move the positive Q1 over to the other side, which is 3.6 microcoulombs from the problem. And so now we can get that charge on the... See, we haven't even touched the electric fields yet, but we can make these relations without having to know the electric fields, because we know how conductors react in a static situation due to a external electric field. And so then this becomes, you have to do negative 1.5, you get 3.1, 2.1. 2.1 microcoulombs will be the total charge in the outer radius. So that's part of the problem answered. But let's go back to actually getting the electric fields. So we can split this problem into parts, like I said at the beginning, and get the electric field in the insulating sphere. In between, in vacuum, that's between the shell and the sphere. And then we already know the electric field inside the conductor is equal to 0, and outside the conductor we also need to get. So for each one of these regions, what we'll want to do is to draw a Gaussian surface, a spherically symmetric Gaussian surface, which will match the symmetry of the problem, of the object specifically, and write down Gauss' law for each part. So let's look at inside the insulating sphere. So this would be the E inside, E for a radius less than A. Right, and that's dotted with our Gaussian area element. And that has to equal to Q enclosed over epsilon naught. So that means what we're doing is we're looking at some surface, some spherical surface that's inside some general radius less than A. So that means we need to know the amount of charge enclosed within that radius. Well, at first it's not obvious what this is, right? Because we're only given the total charge and not the charge density. But we can get the charge density because we know inside the insulating sphere that charges are distributed uniformly. And just like how when mass is distributed uniformly through an object, we can take the total mass divided by the total volume and get the mass density. We do the same thing with charges when it's distributed uniformly. And so we can get a charge density for the insulating sphere, and that would be equal to the total charge, which we're given as Q1, and that will be divided by the total volume of that sphere. Well, we can just plug in the volume of the sphere with radius A. That's the total volume of that insulating sphere. Now this is great. This is charge density. But what we need to solve Gauss's law for the sphere is we need Q enclosed. And that means the amount enclosed at some general radius that's less than A. And what we solve for here is the charge density. But like we said earlier, the charge density is constant no matter where you are in the sphere. So that means if our total sphere is here with radius A, if we have some smaller part of the sphere with some general radius r, which is less than A, then it still has charge density rho, and we can relate charge density rho to the charge enclosed at a certain amount of points, at a certain point, certain radius, right? Like here, we have an expression for rho of the insulating sphere. But if we want to look at some general volume with the volume enclosed being a general radius, a general volume with a general radius where r is less than A, this still has to equal the same charge density since it's uniformly distributed. And we just said that that's also equal to Q1 over the volume of the total sphere. And so now we can relate these two to solve for Q enclosed at some general point, right? And so you'll see that pi will cancel on each side. 4/3 will cancel. And you can multiply the r cubed over. And so you'll get Q1 r over A cubed. And now we can use this here in our Gauss's law for our expression. And just to sanity check ourselves, let's check Q enclosed at its boundaries. So the amount of charge enclosed when the radius of that general sphere here is equal to A should be equal to the total charge on the sphere, right? So if we plug into here r equals A, we should get Q1, and you see that you do. That's one way to check. If you plug in r equals 0, then you get 0 charge enclosed. So it seems to make sense. And the units work out too, which is important. So if you're ever a little confused if something's going to work, you can always go back to unit analysis, and you can also just plug in some values and see if it kind of makes sense given the boundary conditions of your problem. So now we can go back to what we have here, and now we have Q enclosed. And what we want to do, sorry, I just closed the integral. What we want to do here is we can pull out our E outside of the integral, and we can do that anytime that the electric field is uniform over the area element, our dA area element. And we can always do that, say if we have charge distribution that's evenly distributed, then our electric field will also be uniform. So remember that, it's important. So then all this we're left to do here is do our closed surface integral, and this is, so our area element in this case is a small infinitesimal area of a sphere. So you can either evaluate this dA using spherical coordinates, or you can just realize that that the total surface area of a sphere is 4 pi r squared. In other words, it's going to be the radial derivative of the volume of a sphere, which is the same as the surface area of a sphere. So, right? Because if the volume of a sphere is 4 pi r cubed, when you take the derivative with respect to r, you get the surface area, right? Because this is how the volume changes with respect to the radius through its surface area. So anyway, and again, this is some general r where r is less than a, right? Because when you do the left-hand side of the Gauss's law, the dA integration is with respect to your Gauss surface, and your Gauss surface is inside the insulating sphere in this case. So this electric field that we get here is specifically for inside the insulating sphere. And sorry, I didn't carry my r over a. And so we get that the electric field inside the insulating sphere is, you can divide over to 4 pi r squared. So you get Q1 r over 4 pi epsilon naught, and that should look familiar to you. It's a cubed. And this is really the hardest part of the problem. The other parts will not be as hard, I can guarantee. So I will talk about the other parts, but I'm not going to go completely through them. For the second part, you have to get the electric field. Again, you have to get the electric field for each section, and the next section is your Gauss surface will be of some radius in between A and B. So that's the electric field that you will have to calculate for inside the shell, but outside of the conducting sphere. I'm sorry, insulating sphere. Outside the insulating sphere, but inside the volume of the conducting shell. And so that would be a radius that's in between A and B. And for that, your Gauss surface will again be a spherical surface. And so you'll be able to apply the same trick with pulling the E field out of the integral on the left-hand side. And then your Q enclosed is a lot simpler, because at this point, your radius, as it changes from r equals from A to B, there's no more, you're not adding up any more charge. There's no charge that lives in between the shell and the sphere. And so it's just the total charge enclosed, which is from your insulating sphere, and that's just Q1. So when you do the Gauss law for that, the electric field in between the two objects, your Q enclosed is just Q1. And now the only other area you have to do any calculation for is outside the total object. And that will also be pretty straightforward. Again, you're doing a Gauss surface of spherical symmetry to match the object's symmetry and shape. And the total charge enclosed will just be the total charge on the object, which is given to you in a problem as Q1 plus Q2. And so that sums up this problem. If there's any questions on any of this, feel free to reach out to me. Sorry this is late, but I'm hoping you guys can at least check your answers and also use this as kind of a sanity check when you're studying. All right, thank you.